Well, ladies and gentlemen, on behalf of the rector, I'm honored to welcome Professor John Mather in this historical hall of our university, where all the most significant events of our academic life traditionally take place. Professor Mather's research has been for decades at the heart of the efforts to understand and characterize the relic background radiation after its discovery in the mid-60s of the last century. For this reason, and in particular for the Kobe experiment, Professor Mather received, as we well know, the Nobel Prize for Physics in 2006. His observations and discoveries have allowed astronomers to look back into the infancy of our universe and to gain insight onto the origin of our present-day world. It is really fascinating to consider that from his house situated just a couple of 100 meters from here, Galileo Galilei started the exploration of the universe by performing the first astronomical observations with his new small telescope. This happened exactly 402 years ago, in the winter between 1609 and 1610. At that time, Galileo Galilei was professor of mathematics here at the University of Padova, the University of the Venetian Republic, and taught just in this Aula Magna. Since then, astronomy as well as physics have remained disciplines of key interest for our university and our studies. A couple of years ago, we celebrated in this same Aula Magna the 4th centennial anniversary of the first astronomical observations with a large participation of major scientific authorities in the field of astronomy and science, the year of astronomy 2009. But it is now amazing to consider how much the astronomical science has developed and progressed since Galileo's time. In 4 centuries, our knowledge stepped from Galileo's tentative exploration of our closest environment, the brightest objects in the solar system, the Moon, Venus, Jupiter and its satellites, to the detection of light emerging from the earliest evolutionary phases of our universe. Something that even the most lively imagination couldn't have ever conceived at that time. And we will listen today about the two, so to say, bridgeheads of this imaginative path, the beginning and what we may consider the current end point of this fascinating story. We are really grateful to Professor Mather to have accepted our invitation for today, and we really hope that despite his huge commitments, he might consider our further invitation to our high school named Scuola Galileiana, giving a lecture course in favor of our brightest students. And now, if Professor Mather is so kind to come here, I have a little present to you. Okay, if you can step up here. We have a microphone here. Mi apre, per piacere. Mi apre un pochino. Yes, so I have for you to thank you for your presence here. A little booklet on the history of the Padua University, 8 centuries of history. Of course, you know that Padua University has been founded in 1222, one of the oldest in the world. But since we don't want to rest on our laurels, I had also this booklet on the present and hopefully the future of the Padua University. And okay, really finally, this is a medal which is called by us Osella. Osella was a traditional gift by the Venetian Doge, who was the head of the Venetian Republic, to his hosts and ambassadors and so on. Of course, at that time it was a silver medal. Now it's not made by silver, but it has been coined for the World Year of Physics 2005, the year before the year of astronomy, 2006. And so I'm proud also to give you this sign of our great appreciation. So finally, thank you very much, Professor Mather. It's really a pleasure to have you here.
Per la presentazione dell'evento invito anche al podio il professor Franceschini.
Good afternoon. I think that a few words are needed to introduce Professor Mather, but I want to do it with a personal memory of the earliest moment I met him. It was in the College Park. That was in '95, and the year later it was in Tokyo at the IRTS meeting, discussing and celebrating the discoveries of the COBE satellite. And in addition, it was discussing another discovery of the, particularly of the COBE satellite. That was another background radiation with peak emission in the far infrared, so shorter wavelengths than the cosmological background radiation. And there was a lively debate, John, you remember that time, about the nature of this new radiation. And just to introduce you to the fact that John Mather's interest to science, the progress of science, didn't end at all at the time of the COBE discoveries, but he continued in the following decades with the greatest interest and effort by himself. Just a few biographic notes about John Mather. He got his PhD in University of California, Berkeley, in '74, and then he moved to the East Coast and got his first job in Goddard in New York, where he started to work in the development of the COBE concept of a new space observatory to characterize the recently discovered background radiation, cosmological background radiation in the microwaves. A couple of years later, John Mather moved to his current position at NASA Center in Goddard Space Flight Center in Maryland, where he was the study scientist first and then the project scientist of the Cosmic Background Explorer concept, and at the same time the principal investigator of one of the 3 experiments on board of this space observatory, the FIRAS, the Far Infrared Absolute Spectrometer, on board of COBE. Okay. I just want to mention one critical event that this mission was expected to fly on board of the shuttle, but then, as everybody knows, there has been a tragedy about the Challengers that implied a complete revision and rescheduling of the space experiment And in as short time as a couple of years, there has been a complete revision of the mission, and from a heavy and sizable observatory, it has been transformed into a much lighter and smaller telescope, okay, still extremely effective in characterizing the background radiation. Based on COBE observations in the early 90s, Professor Mather and team obtained the first complete characterization of the primeval background radiation. And this radiation is a unique echo, or relic, astronomers have, of the fireball era with which our universe started its evolution. And on one side, Mather and team measure with impressive accuracy the spectrum of this radiation, and discovered that this spectrum is essentially the best black body spectrum that we can find in nature. Okay. As a second, it is remarkable, if I can spend 30 seconds more on this, it is remarkable to consider that this spectrum reveals an extremely fine coupling between radiation and matter, okay? And in spite of that, these photons have those that have the least interaction with matter during the recent 14 billion years or so. So this testifies the extremely good coupling between matter radiation previous to the recombination here during the first expansion phases of the universe. Another major discovery of this mission, on the other hand, was about the so-called anisotropies. That is, how the temperature and intensity of the background change from place to place in the sky. Okay? And the discovery was that these changes were extremely tiny, again showing the extreme regularity of these photons, or this photon distribution, showing essentially the very high level of homogeneity and isotropy of the primeval universe. That is setting challenges to our understanding of how this regularity could have been obtained during the first expansion phases of the universe. We will know much more about that by Professor Mather. Okay? So this discovery started a completely new era for cosmology, and offered a decisive contribution to our physical understanding of the origin of the larger scale structure in the universe, galaxies, stars, and planets themselves. Okay? So a complete self-consistent physical theory was then developed, able to explain in detail when and how the universe evolved from conditions of unimaginable temperature, pressure, and density, and how the universal structure grew under the ruling effect of gravity, as we will know more from his lecture. Okay? The theory is based on the discoveries of John Mather, was definitely one of the masterpieces of science of the 20th century, and a major cultural step forward in our knowledge and understanding of the cosmos. Okay? So, among other things, these measurements also mark the inception of cosmology as a precise science. So, based on these discoveries, John Mather and George Smoot got the Nobel Prize in 2006 for their discovery of the black body form and anisotropy of the cosmic microwave background radiation. By the way, it is interesting to consider that we had 3 Nobel Prizes dedicated to astronomy during the last 10 years, okay? Whereas only 2 more have been dedicated to astronomy during the previous 100 years. Okay, so there is a apparently growing interest in astronomy in the science community at large. So unlike other similar situations, the interest and passion of John Mather for the progress of our scientific understanding of the cosmos did not end with the magnificent COBE discoveries, but continued unaltered and uninterrupted so far. So he has, in addition to having served in many working groups and committees around the world, particularly in US, the NASA, National Science Foundation, and others. He has essentially contributed to studies and investigations for other space missions, like Sapphire, for example. But what I want to remember here is his great work he has done starting since 1995 about the new forthcoming enterprise by NASA, by a collaboration between NASA, ESA, and Canada, CSA, about the, what will be in short time the successor of the Hubble Space Telescope. That is the James Webb Space Telescope, okay, and John Mather has been nominated a senior project scientist of for the James Webb Space Telescope in '95. Okay. This mission is the flagship mission for astronomy that NASA is, together with the ESA and CSA, is organizing since the 90s, and is the major instrumental project for astronomy ever built. It will be the largest telescope in space with a diameter of 6.5 meters that will be deployed in space based on a frontier, let me say, Star Wars technology. Okay, still partially under development. Probably John will tell us more about that. Okay. So this telescope is expected to explore the whole history of the universe, starting from recombination until the present time. It will be particularly dedicated to the mysterious, still very mysterious phase about the emergence of the first light sources in the universe. That's essentially the frontier of current day cosmology and astronomy. Okay. I want to mention that it is worldwide known in the scientific community the key role John Mather had in making this fundamental enterprise for astronomy to survive a number of difficulties from both technological part. Is an extremely challenging technology to deploy a 7-meter class telescope in space, of course, with an accuracy which is comparable to the current accuracy of the Hubble Space Telescope, which is a much smaller telescope. Okay. Astronomers know all the efforts that John Mather has made against the government and against NASA to keep this frontier mission to survive all these difficulties. And at the end, it is supposed now that by 2018, this mission will fly and see the first light. Okay. So thank you, John, for all your efforts. Okay. And for being here with us today.
Well, thank you very much for your kind invitation to come. To give a personal moment, Galileo was my first hero. When I was about 8 years old, my parents read biographies of Charles Darwin and Galileo Galilei to me and to my sister, and I thought science is absolutely a thrilling adventure, a very dangerous adventure, but something I really wanted to participate in, and so it is completely amazing to me to be standing in the hall at the place where Galileo spoke. So it's an absolutely wonderful invitation, and I thank my hosts especially for inviting me. Now, I have a great challenge. I need to tell you the entire history of the universe in less than an hour. So I will skip a few parts. But I will start with a summary of some of the great questions that faced astronomers about 25 years ago, when the 4 great observatories NASA has built were being considered. We wanted to know, how did the universe begin? This was before the COBE satellite had flown, so we didn't know all of the story. We wanted to know How do galaxies form? A galaxy has 100 billion stars orbiting around a common center. We don't even now know really how they formed. So we have to observe this as well as we can. Will we find new laws of physics that govern cosmic evolution? Well, in 1985, we did not yet know for sure about cosmic dark matter, although we had a guess. We did not know yet about cosmic dark energy, and we had many great mysteries in front of us at that time. We would also, and this is still a great problem for us, we do not know how the stars are made. We have a general idea, but we do not know very well about the specific details. We do not know how stars die. Not really. We know that they explode, many of them, but all of the calculations are very difficult to do, and so still there are a great many puzzles about that. So we have to go look. In 1985, we did not know very much about black holes. We know a great deal more now about black holes. We know that there is a black hole in the middle of every galaxy, almost every galaxy. We do not know yet how the planets are formed or how life started here on Earth. So these are still very important questions, even though we've made 25 years of progress. So now I would like to, for those of you who are not scientists, I perhaps will give you a great surprise. When you look in the mirror in the morning, you are looking at the inside of an exploded star. The way that the chemical elements that we are made of were produced in the history of the universe is that the first stars were made of hydrogen and helium. Then they burned the hydrogen and helium through nuclear reactions to produce the chemical elements that we are made of, the carbon, oxygen, nitrogen, sulfur, iron, all the other things that we see around us that were not present in the Big Bang material. When you're looking in the mirror in the morning, just imagine you're seeing the inside of a star. So a little bit about how we know these things as astronomers. We look back in time. Many historians look back in time by examining old books. Archaeologists look back in time by looking at old bones. Geologists look back in time by looking at old rocks. Astronomers look back in time by looking at old light. We see light as it has been traveling to us for thousands or millions or billions of years, and so we see it as it really was. But on the other hand, we have to build a telescope and we get only a very fuzzy image of what was happening a long time ago. So it takes a great deal of imagination and thought and careful argument and logic to produce a convincing story about how it all happened. But we really do look back in time. So how do we know how far we're looking back in time? We measure how far we're looking in space, and we know the speed of light. So we do measure our universe the same way that we did learn in high school or college about geometry. If you draw a triangle and you know one side of the triangle and you know two of the angles of the triangle, you know the entire shape of the triangle. So this is trigonometry and surveying that we learned a long time ago. Many stars, however, are much too distant for this angle to be measurable. So the other method that we have is called the standard candle method. If you see two stars or two candles and they are similar, and you can prove that they are similar, and the only thing that's different is that one is fainter than the other, then you conclude right away that the faint one is farther away, and you can use this as a measurement of distance. So by the combination of these two techniques, we measure distance, and therefore, because we know the speed of light, we also know how far back we're looking in time. The next thing we want to know is how are things moving across the sky. The planets move across the sky, the sun moves across the sky, the moon moves across the sky, and a few stars move enough that people can measure that they move across the sky, but most of them are too slow for us to measure. So the other method that we have is we can tell if a star is coming toward us or going away from us by measuring the change of its wavelength or the change of its color. If you hear a train coming toward us and then passing away, the sound of the train whistle will change. It'll drop as it arrives to us. The same thing happens with light waves, very similar, so that we're able to measure the change of color of stars because they're coming toward us or going away from us. And you might say, well, how do you know what color it was supposed to be? As it happens, nature has given us markers in the spectra of stars. These are called spectrum lines. If you spread out the light of the sun with a prism, and you do it very carefully, you will see that there are dark marks across the spectrum of the sun that come from particular chemicals in the surface of the sun. Hydrogen, calcium, many other atomic elements are found in the sun, and we see this characteristic pattern. If we see a similar pattern in a distant star or a distant galaxy, but the wavelengths are all shifted in a certain way, we say that is because the star or galaxy is moving toward us or moving away from us. So this now enables us to measure the shape of the universe. And this was done in 1929 by Edwin Hubble, the same scientist for whom we have named the Great Telescope. Actually, this law was predicted by Georges Lemaitre, who was, as you know, a Catholic priest and a scholar of physics from MIT in the United States. So, at any rate, these are Hubble's observations. He was able to estimate the distance of distant galaxies using the standard candle method that I showed you, and also to measure the speed of distant galaxies. And so he made this plot. And so almost all the galaxies are going away from us. The speed is positive. And you see this tremendous trend here that the farther away the galaxy is, the faster it's going. So if you divide the distance by the speed, you get the age of the universe. So in 1929, the expanding universe was quite clearly demonstrated by Edwin Hubble's observations. You might remember 1929 as an important event in economics. It's the year that the worldwide economy collapsed. I hope that we do not do that again. I think we should learn from the lessons of the past. But at any rate, for science, this was a tremendously exciting thing. It was front page news in the newspapers around the world, and many people were completely stunned and amazed that the universe would be expanding. Albert Einstein had not predicted this. He disagreed. He asked his friends, other astronomers, does the universe expand? Of course, no one thought so. But in 1929, this was an amazing discovery. Now, what else happened after that? Wanted to show you some of the people who were thinking about the early universe. See if my computer will work here. Hold on just a minute. The computer is thinking. Maybe the computer is not thinking. We're having a problem with the computer. We'll see if it wakes up in a moment. Otherwise, we'll have to start over, and I'll have to tell you a story. Problem, we have to reboot the computer, I think. It's not responding anymore. I will restart. Yeah. It won't respond. It's not responding. Not responding. Okay. We'll have to restart. Well, while the computer is thinking, I will tell you a little bit more about the discoveries of the early universe. Einstein was telling us that there was no expanding universe, and these other men were telling us that the universe is expanding. The techniques of astronomy were developing. After the discovery of the expansion, then, of course, we had a great period of time where little scientific progress was made because there was a worldwide war of many sorts. After the World War was finished, people started again to think about the Big Bang, and it was predicted that the universe should be filled with heat radiation from the Big Bang itself. The heat of the primordial explosion should still exist. It should still be extremely bright. In fact, if you put out a square meter of collecting area, you would collect a total power of 3 microwatts. It's extremely bright, this cosmic background radiation. It's just difficult for us to measure. So now I think the computer is coming alive again. Just a moment. So the computer is thinking slowly. Anyway, so the universe is filled with this cosmic background radiation. It was predicted in 1948. The temperature was predicted to be 5 degrees Kelvin, which is very, very cold, but it still means that this radiation would be the brightest radiation of all kinds in the universe, and the great reservoir of heat of the early universe. So now let's see if the computer will recover. So the heat is left over from the Big Bang. It fills the universe. It should come equally from all directions about if it's really cosmic. That would be the great evidence that it is cosmic. I think the computer is coming back. Okay, this is where my story was interrupted. I have pictures of the people who I was telling you about. There is Alexander Friedmann and George Lemaitre, who predicted the Big Bang before it was observed. There's Albert Einstein, who told us that it did not exist. He was quite surprised. Now, these three men, George Gamow and Robert Herman and Ralph Alpher, are the people who in 1948 predicted that there should be the cosmic background radiation. At that time, it was difficult to measure. In fact, people thought that it was impossible. Nobody really tried in 1948. It was discovered in 1965 by people who were not looking for it, but who were brilliant engineers and scientists, and discovered it, and they received the Nobel Prize for that discovery. Now, a little bit more to tell you. The chart that I showed you from Edwin Hubble tells us that there is no center of the universe. If you imagine what the other astronomers living in other galaxies would calculate, here I have my three astronomers. This is us. This is human astronomers looking out, and we see the expanding universe, and this is the speed measured by us. So we calculate that our universe is 1 hour old. But now imagine that you are the tortoise astronomer, and you make the same calculation. You also calculate that your universe is 1 hour old, and you think that you are in the middle. So the conclusion is that there is no center of the universe. All astronomers in all galaxies will think that they are at the center. So that means there is no center. So you will ask me probably, where is the center of the universe and where did it happen? And the answer is, it happened everywhere. Everywhere. There is no center that we can discern. It also means that I cannot draw you a picture. If I could draw you a picture, it would mean that I was standing outside the universe, which I cannot do. So this is the best I can do to draw you a picture of the expanding universe. So you could say, well, maybe I believe this story about the expanding universe, but why am I here? In my universe, my life here on Earth, I do not see any signs of the expansion of the universe. This is the story astronomers tell us, that gravitation is a long-range force, and it reaches across the universe. It is able to stop the expansion of certain portions of the material. So gravity reaches out, it pulls back on material and makes it fall back in to produce a galaxy or a star or a planet. And so that's possible. And because stars can form, then it's possible for the chemical elements to be produced. And therefore, as soon as the chemical elements of life are produced, then it's possible for planets to be formed that could possibly support life even in the very early universe. It's a speculation, it's a guess on our part, but we imagine this is true. So this complexity is what also enables the complexity of life here on Earth. This is what overcomes the second law of thermodynamics, because basically the universe is unstable in many, many ways. So the universe is spontaneously set up so it will form complex structures. So here is a summary of the early history of the universe. We have a picture, as seen from where we stand, of the Big Bang. And this is the map that was made by the Cosmic Background Explorer satellite. We have a story that says the galaxies were formed by small things merging together, just as rivers form from small streams. We even have a picture of a nearby galaxy. This is called the Andromeda Nebula. It's not very far away. It's a few million light years from here. And it's very much like the Milky Way galaxy that we live in ourselves. It even has two satellite galaxies that are in the process of falling into the Andromeda Nebula, just as we have 2 satellite galaxies that are falling into the Milky Way. So here is a summary of the history of the universe. This is the new name for the Big Bang. It's called the horrendous space kablooey. This is, I suppose, American slang, but this is the name that was given to it by a cartoonist who draws the Calvin and Hobbes cartoon strip in the United States. At any rate, I like the name better than Big Bang because it suggests that actually all of space is involved in this expanding universe, and not just that there was a thing like a small grenade exploding. So the beginning started off with an exponential expansion, so we think a very rapid expansion, which produced all of the conditions that lead to our present universe. So it produced the hot and cold spots that we have now observed. Antimatter was produced along with ordinary matter, produced some dark matter, we don't know what it is, produced the dark energy, we don't know what that is, but we do have a measure of the age of the universe, 13.75 plus or minus 1% billion years ago, according to the WMAP mission, space mission that was built after the Kobe. So very shortly after the beginning, all of the antimatter was annihilated by ordinary matter, and so our kind of material, which we're made of, remains. 3 minutes later, the helium nuclei were formed from the nuclear reaction of protons with neutrons, and that was the end of the primordial nucleosynthesis. That's all that we have left from that time. The next chemical elements were not formed until stars could be formed many hundreds of millions of years later. So when the universe was about 400,000, about 389,000 years later, it cooled enough so the atomic nuclei of hydrogen and helium could bind with the electrons, and suddenly the primordial material became transparent. Because it became transparent, we're now able to observe the cosmic microwave radiation, the primordial heat that has now been traveling without hitting anything ever since that time. So it travels for 13.75 billion years until it reaches our instruments, and so we are able to make a map of the early universe. Then there is what we call the cosmic dark ages, and we do not know what happens, but probably not very much. And then finally, after a few hundred million years, we think that the first stars would have formed. This is speculation on our part. We have never been able to observe it. We have calculations and simulations in computers, but it is one of the great ideas that is to be measured and tested by further work in astronomy. So then we think that we know how galaxies formed a little bit. I'll show you a movie of how it might have been. And then our own galaxy formed the sun. So our solar system, by the way, is formed 4.567 billion years ago. And about the same time, the dark energy that we have measured recently caused the universe to begin to go faster and faster. It's 5 billion years ago. So a quite amazing story of the early universe. Now I want to show you a few surprises about the history of the Earth. This is not my personal work, but I'm completely fascinated by it. It is thought that the solar system was formed 4.567 billion years ago, and we have this amazingly precise measurement from radioactive materials. And it is also thought that the moon was formed when a small body about the size of Mars collided with Earth in a collision maybe 90 million years later, and that the Earth and Moon system are the result of that great collision. Then I'll show you another simulation of how the early solar system may have changed with time. It is thought that the planets rearranged a bit because the orbits are not necessarily stable. I'll show you a movie of that might have been. Then because there were rocks hitting the Earth, comets hitting the Earth for hundreds of millions of years, it would have been a very difficult time for life to exist here on Earth. But as soon as that stopped, there is now evidence from geology that the Earth became alive. So this is a remarkable story. As soon as the rocks and asteroids from the sky stopped falling, we got life here on Earth. And by the way, all of the life here on Earth uses the same genetic code, so we are related to the grass and the bacteria. And if there was any other kind, I guess our ancestors ate the other kind of life. So now here's my movie. This is a simulation of the motions of comets and asteroids and planets in the early solar system. So the four big circles here are the orbits of Jupiter, Saturn, Uranus, and Neptune. And these are the comets and asteroids that are remaining from the formation of the early solar system. Now this is a guess, and it might not have been exactly like this, but you'll see after several hundred million years have passed that suddenly the solar system is unstable. And these orbits, which have been going very neatly for a long time, changed dramatically. And you see the comets and asteroids have been almost all expelled from the solar system. And this is a very important event for Earth. This is the why we're not still being hit by comets and asteroids every year. If that had not happened, it's not necessarily true that we could even have life here on Earth. So it's a possibility. We can't prove that it's true, but it's a possibility. So I promised to tell you something about the end of the universe as well. Well, I can't really tell you. But I'd like to celebrate the fact that we have had 402 years of telescopic astronomy since Galileo. A few predictions: in a few hundred years, we may use up most of the coal and oil here on the surface of the Earth. If you did know the answer, people wouldn't like it. You know, in mythology, there are Cassandra and Tiresias who were punished by the gods for knowing the future. And they knew the future, and no one would believe them. So I think that may happen to scientists as well. In the distant future, geological processes could possibly condense all the carbon dioxide into rock, in which case the Earth would cool down. We're currently very worried about the Earth getting warmer, because it is. Anyway, in the very long term, the Earth will become hotter because the sun is getting brighter. In about 1 billion years, it will become much too hot for us here. And so either we move to another planet or it's over for us. When the sun is another 5 billion years, the sun will become so large that the Earth actually orbits within the surface of the sun. This is a very bad time for life here on Earth. Then the sun will go out and become a small star, a white dwarf star. As time continues after that, the distant galaxies will continue to go away from us, and eventually the sky will become dark. So this is a good time to be an astronomer. Let's see, I wanted to show you, my computer has skipped over the chart here. This is a picture of the satellite, the Cosmic Background Explorer that Alberto was telling you about. This is the one that measured the primeval heat radiation so well. It was launched in 1989, 15 years after it was imagined. Anyway, it had 3 instruments, 2 inside this tank of liquid helium, and 1 distributed around the outside. Anyway, it made several important measurements of the universe. I will just show you the answers that it got. This is a measurement of the spectrum of the Big Bang radiation. The theoretical prediction of the Big Bang theory is the smooth curve, and the measurement, which only required 9 minutes of good data to produce, are the little boxes, and you see that they all fall quite nicely on the theoretical curve. So when I showed this to the Astronomical Society, I got a standing ovation, and it lasted for a long time, and I was completely amazed. It meant a lot. It meant that the Big Bang theory was a good theory. If this had not been true, then we could not believe the Big Bang theory anymore. So a very popular result. Now we know this fits even better. The error bars are tiny, 50 parts per million. So an extremely, extremely good measurement. Now the second major discovery we made is on this chart. And when Stephen Hawking saw this chart, he said that this was the most important scientific discovery of the century, if not of all time. And he said that because, I guess he liked the chart, but this is a map of the hot and cold spots in the Big Bang. This is the entire sky shown, projected onto this ellipse, and the pink regions are a little brighter, and the greenish blue here are a little darker. This is a part in 100,000 hotter or colder than the average. So this is 30 microdegrees Kelvin, warmer or colder than the average. So those are the little hot and cold spots. What they mean is the early universe had places that were 30 parts per million more dense or less dense than the average, and that is the reason that we now exist. If those spots did not exist in this map, we would not be able to explain how we exist. So that's a way in which this is one of the most important scientific discoveries. Without that, we could not exist. So now, by the way, we also know that most of these spots are made by something we call dark matter, which is something astronomers can measure, but no one else can measure. So I think it's true. Now, I got to hear here's the Nobel Prize announcement that was quoted to you for the discovery of the black body form, which is the curve with the little boxes, and the anisotropy, and this is Greek, and it means not the same in every direction, of the cosmic background radiation. So I did get to go to Stockholm. I showed my chart a lot, and got my diploma from the King of Sweden. So this is now the second Nobel Prize in cosmology. The first one was for the discovery of that background radiation, and of course the third one was just given this past December for the discovery that the universe is accelerating. So we astronomers did not expect that the universe was accelerating. We thought because gravity reaches across space that the galaxies pulling back on each other will stop the expansion and eventually slow down. But what we measured was the opposite. So here are the three winners of this year's Nobel Prize, this past year's Nobel Prize. Here is they are in 2006 receiving their prize in Hong Kong. This is called the Asian Nobel Prize or the Oriental Nobel Prize. I understand that a prize was given here, also in Padova, for this discovery long before the Nobel Prize was given to them. So you have good eyesight. So a tremendously surprising discovery of astronomy. Now I want to tell you a little bit about the telescope that I'm now working on. It was mentioned earlier that I'm working on the James Webb Space Telescope. This is the telescope that we're now working on to extend the discoveries of the Hubble Space Telescope by using a bigger telescope that can measure infrared light. You would like to measure infrared light because of several things. One is it comes from the distant universe. The most distant galaxies send out ultraviolet light, but by the time it reaches us, its wavelengths are longer. So we need an infrared telescope to see that. Another reason is that the infrared does not pass through the atmosphere of the Earth, so we need a telescope in outer space. And finally, things that are at a lower temperature, like ourselves, emit infrared, and we can't measure that with the Hubble Space Telescope. So now here is a picture of the new observatory. By the way, it's named after the man who went up to President Kennedy and told him how to go to the moon. And so we honor him for his great success in doing that. At any rate, here is the telescope. It looks like a solar energy concentrator because it's got this big parabolic mirror made out of 18 smaller hexagons. So starlight comes from over here, bounces off the mirror onto this small mirror and into the instrument package here. This big thing here is just a big umbrella, a protective sun shield to allow the telescope to get cold in outer space. So this telescope will operate at a temperature of 40 degrees above absolute zero, extremely cold, much colder than the Hubble Space Telescope, and that's what enables it to be a great infrared telescope. The telescope is being built by NASA in collaboration with both the European and Canadian space agencies. Our prime contractor, the company that's doing the big work, is Northrop Grumman, so they're located near Los Angeles Airport. Instrumentation is coming from around the world, Arizona, some from the European Space Agency, some from a European consortium. There are, I think, 14 European institutions involved in building this instrument, and one instrument from Canada. Operations are going to be in Baltimore, just as they are for the Hubble Space Telescope. So this telescope is immense. It's 6.5 meters across the telescope here. By the way, it will be launched in 2018 on a rocket which is being provided by Europe. The Ariane 5 rocket has been very successful, and it's a very good and powerful rocket for the purpose. The observatory should last for 10 years. We're requiring 5 years, but we're carrying fuel for 10. So I want to illustrate a few of the scientific discoveries people hope to make with this observatory. This is just, by the way, picture of the model that has traveled around the world. It's been in Munich, it's been in Canada, it's been in Washington, been many places, just basically to show you that this is an enormous telescope. This umbrella, this sun shield here, is approximately the size of a tennis court. And it will be folded up to go into outer space. So here is a drawing that shows how the telescope works. Here is the telescope after it's in outer space. There's the telescope, and here's the big protective umbrella. There is the sun on this side. Here it is folded up inside the top of the rocket. We'll show you a little movie about how it unfolds. And here it is orbiting around the Lagrange point, which is 1.5 million kilometers away, farther from the sun than we are. I'll show you a drawing, I think, of how that's arranged. Anyway, it's much too far away for us to go visit with an astronaut to fix it in case we make a mistake, so we have to make sure there is no mistake. Here is a movie that shows you how the telescope will unfold in outer space. This is actually about 10,000 times faster than it really will do it. But first we unfold the solar panels and then the telemetry antenna. Then we unfold the big umbrella to protect the telescope. Then we raise the telescope away from the warm part of the spacecraft. Then we unfold some more of the sun shield. By the way, this is very complex. We know that. We will do a lot of practice and a lot of test. And also, the company that's building it says this is not the most complex thing they've ever launched, and not at all. They have other projects. Anyway, here are the 5 layers of the sun shield being put into place. And after that's in place, then we will unfold the telescope. This is all done by remote control in outer space by motors, little motors. And of course, to make sure that it works, we have 2 motors for everything, or 2 sets of windings on each motor, 2 sets of electronics, 2 sets of everything where it's possible. So there is the telescope as it will be in outer space. So this is a drawing of where the observatory will be. There's the sun, there's the Earth, the moon orbits around the Earth, and then it's a little farther than that out to the Lagrange point L2. This drawing is not to scale. This is 93 million miles, about 150 million kilometers, and this is only 1 million kilometers from here. But at any rate, this is where it will go. The telescope is immense, as we mentioned. There is the drawing of the size of the Hubble mirror, the James Webb Telescope mirror, Spitzer Telescope mirror, and there's also, as you know, the Herschel Space Telescope is in outer space, and its mirror is about this big. It's bigger than the Hubble telescope, so it is currently the largest telescope in outer space. So we have 4 different instruments on board. I won't tell you much detail about them, but they have cameras and spectrometers, so we can make the rainbow that shows you the chemical processes and physical processes in the objects that we discover. Here is a picture of 6 of the mirrors being tested in the cold test chamber at Marshall Space Flight Center. Here they are, all coated with gold. There's about an ounce of gold altogether on this telescope to make the mirrors reflect better. We have done a small model of the telescope to prove that we know how to align it. By the way, when it is launched, it is not the correct shape. We learned from the Hubble telescope how to focus things after launch. And so we use the same kind of mathematics, and we believe that it will work well because we've been rehearsing and practicing on this little model. We have 4 instruments. I just have one of them to show you here. This is the one that's made in Europe. This is from a company called Astrium in Germany, but this is the big spectrometer that will take pictures of 100 galaxies at one time for all the details we need to know. This is based on a quite remarkable device called a micro shutter array. We have 250,000 little tiny shutters, which are about the size of the diameter of a human hair. So here are the shutters being opened up. They can all be opened and closed by remote control from here using magnets. So if you want to watch the telescope being assembled, there is a website, the James Webb Space Telescope, JWST. If you go to the website, you can see what they're doing each day in our in our clean room at Goddard Space Flight Center. We will, by the way, take the telescope down to Texas. This is the place at Johnson Space Flight Center where the Apollo astronauts rehearsed for their moon landing. The test chamber is just the right size for us to put the telescope in and prove that it will focus and take a good image after launch, and it will cool down to the right temperature. Just a few pictures of what we might hope to learn about. In a supercomputer, you can predict how galaxies formed, and here's a simulation of how the first galaxies formed. So hundreds of millions of years and billions of years are passing in front of us here in a few moments. So we can never see this happen with a telescope, but we can try to tell whether this is the correct picture, because the calculations that they make with the computer have to match with the kinds of images we will take with the observatory. So maybe this is a true picture of the early universe, and maybe not. It's to be learned, but you see what a totally amazing and chaotic process it is. Another thing that we know happens is that galaxies collide with each other. By the way, the Andromeda Nebula, which is only a few million light years away, is coming in our direction, and in about 5 billion years, it will do this. It will collide with our own galaxy, and something tremendous will happen. It will be a wonderful time to be an astronomer because you will see collisions of all kinds. Now, we don't know whether the sun will be expelled from the Milky Way galaxy and go flying off into outer space like these, or if it will fall back into the center and become part of the middle of the new galaxy. But you see they're about to join together, these two beautiful galaxies. So this could be our future. In some 10 or 20 or 50 years, perhaps we'll know whether it really is. There are things astronomers can measure that will tell you whether this is our future or not. So a few other things we can measure with the observatory. Nature has given us lenses in space. The gravitational force of these beautiful yellow galaxies here actually magnifies the image of another galaxy over here. So nature has provided an extra lens for the telescope. So this is a galaxy much farther away than the others. It's been magnified. So one of our most important tools is to be able to extend the reach of our telescope by using nature's telescope. Another thing we want to do is to look inside clouds like this. This is what we call the Eagle Nebula, and this is a place where stars have just been born very close by to us. We cannot see inside. You see the stars are on the outside and the clouds are opaque. But if you use infrared light, this is the same place in the sky. You can see through the dust, see inside, to see how stars are being born as we speak. So it's still a great mystery. We also have the hope of seeing planets. This is a picture taken by the Hubble Space Telescope. There's a star called Fomalhaut in the southern sky, and here's a little spot in the cloud of dust around it. This is a cloud of dust, and it was predicted that there should be a planet in here to give this dust cloud this ring shape. Anyway, here is the planet. It's been seen twice in 2 different years, so we know that it's even orbiting around its star just like a planet should. So this is the first time since the discovery of Neptune that a planet has been predicted and then detected in the place that it was forecast. There are a few pictures that we also do a few wonderful things from the ground using what's called adaptive optics. But at any rate, this is one of the great challenges of astronomy today, is to study planets. We even have, and this is a very important thing we hope to do, once in a while this happens. We're watching a star and a planet goes between us and the star and blocks some of the starlight, so the star appears to get a little bit dimmer. This is very important to us because we've already found more than 1,000 stars where this happens. And also, some of the light from the star passes through the atmosphere of the planet on its way to the telescope. So it's possible then to study the contents of the atmosphere. And we've already learned that various chemicals exist in other planets. around other stars. So eventually we hope to find an Earth-like planet circling a sun-like star and be able to tell that it has things like water in the atmosphere of that planet. So it's part of the search for our own history to learn how the Earth could come to be and to have a water on its own surface. So this is what one of the great quests of astronomy these days is to look for planets around other stars. Of course, we don't always have to go out of the solar system, so I like to remind people that there is a planet, a satellite of a planet. This was actually discovered by Galileo himself. It's one of the 4 bright satellites of Jupiter, and it has an ocean, and it has ice over the ocean, and it's quite possible, according to biologists, that there is life in that ocean under that ice. So one of the great quests for astronomers also is to go land on the surface of this object and drill in and see if there's any sign of life inside. Now, this is exceedingly difficult. It's much more difficult than building a telescope, but some future astronomer, we hope, will be able to do this question as well. So there is much more to know. We'll conclude here by saying you can go to our websites. This is the one for the telescope. This is our one for cosmology. The Nobelprize.org has wonderful documentation of all of their prizes. And of course, I have a little book which has been updated now to tell the story of cosmology and of the new telescope a little bit. So thank you very much. I will be happy to answer questions if people have them, so do not feel shy. Thank you very much. Anybody who has a question, please feel free to have a question. Otherwise, we can do informal things afterwards with the students. Okay.
First of all, thank you very much for your very bright and interesting lecture. So long life to Hubble Space Telescope, but long does not mean eternal. And the best possible success to JWST. But what is your opinion if we will, what's your opinion about ultraviolet in the next decade?
Okay. So the question is about ultraviolet astronomy after Hubble, I suppose. The Hubble telescope is probably going to last for 5 or 10 more years, but it's unknown, of course. Eventually, by the way, the Hubble telescope has to be safely disposed of. We cannot allow it to fall on Padova, which it might do. So eventually we have to produce another telescope in outer space to do ultraviolet astronomy. We cannot do ultraviolet on the ground. So right now there is no particular American plan for that purpose, and I think when the Hubble is finally over, then we will know what to do. But right now there is no plan. Many ideas, but no plan. Another question. Hi, Para.
John, thank you again for the brilliant conference. But my question is similar to the one just asked. Your title is From Beginning to End. Looks to me is easier to predict the end than the beginning because you are stopped at the last scattering surface. I mean, you cannot see anything beyond that. Now, what's your opinion about trying to know more about what happened before by using gravitational waves? Okay. And what is your opinion about the position of NASA about that? It seems to have abandoned the idea to go on with LISA.
Okay. So the question is about gravitational waves. As many of you know, the NASA and the European Space Agency were planning together to fly an observatory called LISA, L-I-S-A, which was to search for gravitational waves from black holes and various other exotic processes. There is also the possibility that gravitational waves might come from the very early universe. It's a separate subject, but related. Both of these now have to be changed because we're not able to do them right now. European Space Agency, I think, is in the process of flying a technology demonstration mission for the first one, for the LISA. And so I'm not sure what will happen after that, but I expect that's a very high priority thing. The other question about gravitational waves from the Big Bang itself is an open question, and there are at least two ways to approach this topic. One is to measure the polarization of the cosmic microwave background radiation. And so numerous satellite missions have been proposed that could do that, and many people are trying to measure it from the ground. So much progress is being made. I don't know how soon we will fly a satellite to do that, but I think it will happen. I think there's no other way to get that information. And similarly for the gravitational waves, there's no other way to get that kind of information. So maybe we can't do it this year or even this decade, but it will be there when we get there, and we need to continue to plan for it. That's my opinion. By the way, Piero was one of the first people to work with in Europe for me when we were beginning to plan the James Webb Space Telescope. So good to see you.
Thank you.
Okay, well, maybe if no more questions, then we'll get a chance to talk with the students later. So thank you very much. Thanks again for coming.